I welcome you all in this course on power plant engineering. Today we will solve some of the numericals based on the hydropower. The first numerical I am taking up for the forces on the curved plates. It is a jet discharges 150 liters per second of water with velocity of 70 meters per second, impinging without shock on a series of curved vanes. So there are series of curved vanes and the jet is impinging without shock on the series of the curved vanes. These vanes move in the same direction as the jet. When the vanes are moving in the same direction as the jet, it means the inlet angles, all inlet angles are 0. The shape, it is not shell, this is shape of each vane is such that it would deflect the jet through an angle of 150 degree. So when the jet is moving in this direction, so after striking the or after sliding over the vane or after striking the vane, it is deflected at 150 degrees and 150 degree from the direction of motion. The surface, the surface friction reduces the relative velocity by 8% because the vane surface will certainly offer certain resistance, and that will reduce the relative velocity by 8%. As the water passes across the vane, and there is a further windage loss equivalent to 0.5 u square by 2 Newton meter per liter of water, u being the vane velocity. Find velocity of vane corresponding to the maximum efficiency, value of this efficiency, I mean the numerical value, forces on the vane, power output, right. So, first of all we will consider a vane is something like this, and jet and the vane are moving in the same direction. So the shape of the vane is like this. So inlet angles are all are 0. This is V, U, and VR is simply V minus U. This is relative velocity. And then jet is leaving the vane. It is deflected by 150 degree. This is 150. And then the vane again is moving in this direction U, and then difference of this will give the relative velocity. So first of all, relative velocity at the inlet, that VR is V minus U. Now V is given here 70 meters per second. So V minus U is equal to 70 minus U. That is the relative velocity at inlet. Definitely the relative velocity at outlet, that is VR1, is going to be, because 8% losses are there, so it is going to be 0.92 V minus U. Okay. Now whirl velocity VW is equal to V is equal to 70 meters per second, and VW1, whirl velocity 1, is equal to U minus VR1 cos, because this angle is going to be 30, and suppose this is U, and then this is going to be the V1, this is VR, so it is VR cos 30, right. Or we can say that it is going to be equal to U minus VR1, we have already calculated 0.92 V minus U under root 3 by 2. This is VW1. Now the work or power output, because we are saying work, because rate of work we will be calculating, because we are assuming mass flow rate, right. It is VWU minus VW1 U1. It is always like that. Okay. So in that case, mass flow rate VW is V minus, because here U is equal to U1. So U will take out. So V minus U minus 0.92 V minus U under root 3 by 2 u. If we simplify this expression, it is going to be mass flow rate 1.797 V minus u multiplied by u. That is the work output, rate of work output. Right? Now, you look at the numerical, the deflection is 150, right? Velocity is 70 meters per second. So, what we have done, we have first calculated the relative velocity at inlet. After relative velocity at inlet, we have calculated relative velocity at outlet. Then whirl velocity, because inlet angle is 0. So, whirl velocity is going to be, and for the outlet, we have calculated whirl velocity, because this is relative velocity of the fluid which is going out, and it is deflected at 150-degree angle, right. So, this angle is 30 degree and this angle is also going to be 30 degree. This is the vector for peripheral velocity. So, this is the absolute velocity through which the fluid is leaving the vein. Now, the horizontal component of this velocity is this one. So, we have taken u, this is total u, minus VR1 cos theta. So, this we will be getting this vector, right. So, this is how we got the whirl velocity at the outlet. Value of u is equal to value of u1, right, for the vein, and then we got the output. Now, after getting the output, this is the theoretical one. Now, we have not taken into account the losses, these losses. So, if we take into account these losses, then net output is going to be equal to mass flow rate 1.797 V minus u multiplied by u minus again mass flow rate u square by 2, that is it, because it is a 0.5 u square by 2 into 0.5. Okay, it is 0.5 u square by 2. So, mass flow rate. So, this is the net output we are getting. And as you know, the incoming energy is the kinetic energy of the jet. So, kinetic energy of the jet is half m v square, right. So, efficiency is going to be equal to work net divided by kinetic energy. This is the net work. So, mass flow rate multiplied by 1.797 V minus u multiplied by u minus 0.5 u square by 2 divided by kinetic energy, that is half m v square. Now, this m will be cancelled out, and efficiency expression we are going to get 3.594. Now, uv divided by v square will give u by v minus u square by v square minus 0.5 u square by v square. What we have done, we have simply multiplied this 1.797 by 2 and divided this v u divided by v u divided by v square. So, it is u by v, and then minus u square by v square has come here. Similarly, minus u square by v square has come here. Now, u by v, if we consider u by v as rho, speed ratio, then efficiency is 3.594 rho minus rho square minus, this is multiplied, sorry, 3.594 rho minus rho square minus 0.5 rho square. It can further be simplified as 3.594 rho minus 4.094 rho square, because 3.594 plus 0.5. So, it will automatically become 4.094, and that is efficiency. Now, after calculating this efficiency, we have to find maximum efficiency, velocity of the vane corresponding to maximum efficiency. If you want to find the maximum efficiency, we will have to differentiate this term with respect to rho. So, first of all, we will write efficiency is equal to 3.594 rho minus 4.094 rho square. Now, we will differentiate this with respect to the rho. So, dN by d rho is equal to 3.594 minus this multiplied by 2 will become 8.188 yes rho square. Okay, and when we are putting this is equal to 0, sorry, this differentiate this rho square will not be there, only rho. So, when we are putting this is equal to 0, then we will be getting the value of rho as 3.594 divided by 8.188, and this is going to be equal to 0.439. Now, U by V is 0.439, therefore, U is equal to 0.439 multiplied by V, and V is given here 70 meters per second. So, 0.439 into 70, it is going to be equal to 30.73 meters per second. That is the peripheral velocity. Now, once we know the peripheral velocity, we can find the maximum efficiency. It is simply 0.439, that is rho, 3.594 minus 4.094 into 0.439. We have used the similar formula. We have used the similar formula, right? And now from here we can get the maximum efficiency, and maximum efficiency is 0.789. We multiply it by 100, we will get 78.9%. That is the maximum efficiency. Okay. So, this one we have already calculated. Now, the B part is value of the efficiency we have calculated, velocity of vane corresponding to the maximum efficiency we have calculated, velocity of the vane corresponding to the maximum velocity is 30.73, right, and value of this efficiency has turned out to be 78.9%. Now, force on the vane. The force of the vane, first of all, force in horizontal direction. It is very simple to calculate. It is mass flow rate multiplied by VW minus VW1. That is the force in the direction of movement. Now, here the discharge is 150 liters per second Q. 150 liters per second means it is 0.15 meter cube per second if we convert it into the cubic meter. So, it is going to be 1000. We are assuming here, because density of the water is not given. So, here we are assuming density of the water as 1000 and multiplying it by 15, and 15 is Q. It is 150 LPS divided by 1000. VW is 70 minus VW1, 30.73 plus 0.92, 70 minus 30.73. I am just putting the values under root 3 by 2. And from this, we will be getting 10,5,105.83.7 Newton or 10.58 kilonewton. That is the force which is exerted on the vane in the direction of the motion, right? Because there is a change in relative velocity. So, there is going to be the y component, Fy, right? So, the value of Fy is again mass flow rate and Vr1 sin theta. Sin theta is here, sin theta is 30, because in this vein the situation is like this. The movement of the fluid is like this. So here, because the moment is horizontal in only in x direction, there is no force in y direction. The force exerted in y direction will be through the exit velocity only, or exit movement of the fluid only. Now again we will calculate 1000 into 0.15 into again 0.92, 70 minus 30, and sin 30 is half, and this will give the force 2709.6 Newton or 2.7 kilonewton in y direction. Now power developed, I think last one is the power developed, power output. Now again the power output will just force multiply force by the peripheral velocity, right. So in this case power output P is going to be again 1000 into 0.15. This will give the mass flow rate multiplied by 1.797 V minus U multiplied by U, and this is minus 0.5 U square by 2G. This formula we have already derived, right. Now we will simply putting the values, that is 150, 1.797, 70 minus 30, not 70 minus 30, I think previous 3073, not 30, 3073, 0.73 minus 0.5, 30.73 whole square by, now this is not G, G will not come here, multiplied by 2. Okay. And this will give the power output as 289,872 watt, or sorry 289 is not, it will come around 289.9 kilowatts. Okay, you just divide by 1000 and this is the final value which we are going to add. So in this numerical, this is going to be 289.9 kilowatts. Now we will take another numerical which is based on the Pelton wheel. Now in a Pelton wheel, it is a large Pelton turbine. So these are the design particulars. Head at the distributor 630 meter. So this is the head, water head is available, and this head is normally generated by making a dam, right. Discharge power developed. So discharge is 12.5 meter cube per second, and it is developing 65 megawatt of power. Speed of rotation is 500 RPM, speed of rotation of the wheel. Runner diameter is 1.96 meters, it's approximately 2 meters. Jet diameter and number of jets. So jet diameter is 19.2 centimeters and there are 4 jets. As I told you in my previous lectures, in a Pelton wheel, it is not necessary, it has to have only one jet. There can be n number of jet in a Pelton wheel. So here there are 4. Angle through which jet is deflected by the bucket is 165, and that is the most desired angle. Mechanical efficiency of turbine is 96%. Mechanical efficiency is the output and the hydraulic power developed in the turbine. So that is the mechanical efficiency. Output means power available at the prime mover shaft. Determine power loss in the distributor nozzle, power loss in the distributor nozzle assembly and the buckets together. So at the entry some power is available and there is an assembly and which distribute fluid in different nozzles. So because there are bends, there are change in directions, so some losses are bound to be incurred there. So those losses have to be found out, and if Loss in bucket is proportional to VR square. Determine the best speed for this head and discharge. So, for this numerical number 2, first of all, mechanical efficiency. As we know, for Pelton wheel, mechanical efficiency is power output, power available at the shaft, and power developed in the vanes. And that power is m v minus u 1 plus k cos phi. This is the power which is developed in the vanes. Now, here mechanical efficiency is 96% and power is 65 megawatt. So, power is 65 megawatt and mechanical efficiency is 0.96. So, 0.96 is equal to 65 into megawatt means 10 to power 6 watts. Mass flow rate V minus U 1 plus k cos phi here it will be multiplied by U also. It is work, not force. It will be multiplied by U also. So, mass flow rate V minus U multiplied by U 1 plus k cos phi is equal to, if we simplify this, we will be getting 67.71 into 10 to power 6 watts. Right? Now, the power supplied. Now, this is the power which is available, which is developed in the blades. Now, what was the actual power available? Actual power available was mgh. mgh means rho q gh. And rho q gh is, rho is, let us assume 1000, q is how much? Q is how much? 12.5 meter cube per second. 12.5 into 9.81 and h is 630. So, this power is coming as 77.25 megawatt. If you divide it by 10 to power 6, then it will come as 77.25 megawatt. Power developed in the vanes is 67. So, this is the difference and this is the loss which is incurred in the distributor, right. So, power loss in distribution nozzle assembly and the buckets is going to be equal to 77.25 minus 67.71 into 10 to power 6, or it is going to be equal to 9.54 into 10 to power 6 or 9.54 megawatts. This much power has been lost in the distributor and the nozzles. Now, head loss in the buckets. Now, head loss in the buckets is proportional to VR square. It is mentioned, it is proportional to the VR square. So, head loss is equal to a constant VR square. VR is relative velocity at inlet, right, and that is going to be C V minus U whole square, because in a Pelton wheel, if you remember, the shape of the bucket is like this and the jet is striking in the middle of the bucket and the bucket is also moving in this direction. So, if the jet is striking with velocity V and bucket is moving with velocity U, then head loss is, the relative velocity is V minus U, right. Now, Q per nozzle is equal to 12.5 by 4 meter cube per second, right. Now, this Q is given, then from this Q, diameter of the nozzle is also given 19.2. So, diameter of the nozzle is given 0.192 meters, right. So, the velocity can be calculated as 12.5 by 4 into pi by 4 into 0.192 whole square, 192 square, and this velocity is 107.93 meters per second. This is velocity at inlet. Now, peripheral velocity u is equal to pi dn by 60 is equal to pi, diameter is what is the diameter? 1.96. So, 1.96, n is 500, rpm 500 and divided by 60, and that is going to be equal to 51.31 meters per second. So, now we have the velocity at inlet, absolute velocity at inlet, and peripheral velocity also. So, head loss is equal to a constant c, v minus u is equal to constant c 107.93 minus 51.31 whole square, and that is going to be equal to 3206 c, that is head loss. Now, for the maximum efficiency we know that u is equal to v by 2, u is equal to v is equal to 2u, right. So, for the maximum efficiency the head loss is, now away from this, suppose we want to have maximum efficiency, in suppose if maximum efficiency is there, what is going to be the head loss, right, because here in this question it is, in the last it is asked, determine the best speed for this head and discharge, right. So, head loss for the maximum efficiency is going to be v is 2u minus u multiplied by c is equal to cu square. So, for the maximum efficiency u has to be equal to 56.62 meters per second, right. Now, once we have the value of u, we can always find the value of n. N is equal to 60u by pi d, and from by putting this value of u, pi and d, we will get 552 rpm. So, if we run the turbine at 552 rpm, and that is going to be the best speed, or where the efficiency is going to be the maximum for the given head and discharge. There is also one more numerical on a Francis turbine, right. An inward flow turbine reaction type with radial discharge. So, it is a Francis turbine with an overall efficiency of 80%, required to develop 150 kilowatt of power, head is 8 meter, peripheral velocity of the wheel is 0.962 gh, that is u, radial velocity of flow is 0.36 under root 2 gh, wheel is to make 150 rpm, and the hydraulic loss in the turbine are 22% of the available energy, angle of the guide blades at inlet, wheel angle at inlet, diameter of the wheel, width of the wheel at inlet. So, for this numerical number 3, overall efficiency is given 80%, H is given 8 meter, power 150 kilowatt, and N is 150 rpm. So, first of all we will calculate u using this formula, because H is known to us. So, when H is known to us, that will give the velocity of u as 12.03 meters per second. Then we will calculate Vf, velocity of flow. For velocity of flow, the formula is given. So, velocity of flow is again 4.51 meters per second. Now, this overall coefficient which is given here, it indicates the overall efficiency. Now hydraulic losses are 22%, so hydraulic efficiency is 88%, and this is equal to VWU by GH. Now if you put the value of U, G and H, from here we will get the value of VW as 5.09 meters per second. We have to find angle of the guide blade at inlet. In order to find the angle at the guide blade and inlet, so the inlet triangle, if we draw for this, it is going to be like this, suppose, or it can be like this also. Normally it is like this for Francis turbine. This is V1, VR, sorry, this is U, U1, sorry, this is U, 1 minute. So inlet triangle for a Francis turbine is like this. This is U, this is VR, and this is V, right? So inlet angle is going to be VF by tan alpha is going to be equal to VF by VW. VF and VW we have already calculated. It is 4.51 divided by 5.09, and this will give the value of alpha as 41 degree 33 seconds. Now tan pi minus theta. Tan pi minus theta is going to be the VF divided by U minus VW. This is U and this is VW. And this will give the theta as 147 degree. Right? So both the angles we have calculated. Wheel well angle at the inlet, angle at the guide wheel, and diameter of the wheel. So in order to find the diameter of the wheel, you'll use again the same formula, pi d n by 60, pi into d, n is 150, divided by 60 is equal to 12.03. This will give the diameter as 1.532 meters. Now the last one, width of the wheel at inlet. So for the width of the wheel at inlet, we'll go by the overall efficiency. It is P by power available, that is mgh. So rho q gh is equal to 0.8, and this is equal to 150 into 10 to power 3 divided by 9.81 into 1000 into q into 8, that is going to be equal to 0.8. This will give the value of q, that is 2.389 meter cube per second. Once we have the value of q, flow rate, then q is equal to always pi dB Vf, area multiplied by velocity of flow, and that is pi into 1.532 into b into 4.51, because we have already found this velocity of flow previously, and diameter also we have calculated, and this will give the value of b as 0.11 or 110 millimeter. So width of the wheel at inlet is 0.11 meter. That is all for today. Thank you very much.